One of the typical bets that you would take on the system that we've been developing is, for example, what kind of socks or what color socks would Ronaldo be wearing in his next match? I joined BBD while studying computer science at the University of Pretoria, and I've become very passionate about cloud computing. I've recently become certified as an Amazon Web Services developer and solutions architect on an associate level. So what is this talk all about? It's about running applications that are highly available, globally scalable in minutes, resilient, cost-effective, as well as secure. So in order to understand what this talk is all about, there's a few background concepts that we need to speak about first. First of which is containerization, using a very popular technology these days called Docker. So what does Docker do? It essentially packages an application as a whole with all of the parts it needs. You can think of this, for example, if I'm developing an application that has a dependency on a specific version of Python, for example, and I need to deploy it. Now I need to go make sure on every host that I'm deploying this to that that specific version of Python is actually installed correctly. With Docker, all that you need is the Docker daemon running. So you can think of a Docker container as virtualization on an operating system level, but it's not exactly a virtual machine. It actually uses the host resources directly. It's an open source platform to run distributed applications, and this forms the very backbone of Kubernetes. You can think of a Docker image as a class definition and a container as an instance of that class in the OO paradigm, but essentially this is now just for infrastructure. The second background concept that we need to speak about is called microservices. So it can be argued that microservices is a flavor of the services-oriented architecture, but with a few major differences. If you regard a typical multi-tiered architecture where you perhaps have a three-tier architecture with a presentation layer where you might perhaps run an Angular or some JavaScript application for web applications, a logic tier for where I perhaps have RESTful APIs deployed, and then also your data tier where you have persistent storage, maybe a Postgres database or something like that. With microservices, we say we want to loosely couple these services by not sharing any data between them. Also importantly, microservices make use of technology-agnostic protocols, or can make use of them. This allows you to build what is called polyglot microservices. So depending on the specific skills of the team that is developing a specific microservice, I can allow them to code in whatever they want. You can code in Python, you can code in Java, you can code in C#. Also importantly, a single microservice is deployed, developed, and tested in isolation, which allows for vast agility in my development process. Microservices also attempt to encompass the single responsibility principle. So in other words, I do one thing, and I do it very well. So why do we go microservices? Why is it so popular? You get this functional decomposition, which allows for failure isolation. If I think about a typical system, let's say, for example, I'm building an insurance system where I have a quotes section. There's a whole process that needs to take place for a quote to be done. With microservices, if a specific part of that system has broken, and somehow a bug has gone into production, and it's gone through all my unit tests, all my integration tests, and even some manual testing. If this does happen, then that's only that very, very, very granular piece of my system that's broken. It also allows for fast and agile development, because now, with a microservice, it's a very small piece of functionality that I, as a developer, need to understand. It also facilitates less regression testing because my microservices using these technology-agnostic protocols, something like HTTP for REST, for example, can communicate on version service contracts, where if I deploy a new version, I can essentially just speak to this older running version in that specific service contract. And I mentioned fast development. I can have independent development teams working on a specific microservice without that dependency that I have, oh, I'm waiting on somebody else. It facilitates granular, horizontal scaling. So in terms of scalability, you essentially get three dimensions of scaling. The popular choice for a single process application would be to scale up, or vertical scaling, where I add more resources, I add more memory, I add more CPU. Whereas with horizontal scaling, that's facilitated via replication. So if I have an application that needs to service 1,000 requests coming in from somewhere all across the world, now I can horizontally scale and say each of those applications now only has to service 500. But microservices are great, but they also come with many challenges. A very profound one is configuration. So with a typical single process application, I only have to configure that one specific thing. But now I have 100, I have 1,000 microservices running in parallel across various development environments. I might have 1,000 in dev, 1,000 in QA, and then 1,000 in all of my different, perhaps multiple production environments, each of which is required to be configured. It's also a major mindset change, developing microservices. Because if you get the challenge of, I need to develop this piece of business functionality, I think of the whole process as one thing. With microservices, you need to determine what is called service boundaries, where it tries to encompass that single responsibility principle where I might need to work together with 2 or 3 microservices to accomplish this piece of business functionality that I need to develop. And interestingly enough, business reuse or business module reuse is no longer as key. And this goes a bit against our training that we get when starting to learn how to code. Because a microservice is so small, it can essentially, in some scenarios, be seen as throwaway code. Also, deployment of these services can be very complex. I now have 100 different services that need to speak to one another, and I might perhaps not be running on a single host. I might be running on 6 or 7 hosts. How do I decide where to deploy my applications to so that they integrate, so that the load is spread evenly amongst them? Microservices also come with significant operational overhead. So I have these 1,000 services now running somewhere. How do I monitor them? With a single process application, that's very easy to do because it's only that one thing that I care about. Log aggregation and searching is now also very important. If something goes wrong, I want to go look at my log files and I want to do a Control F and see where is the error message that was logged, where is the warning that was logged. But now I have 1,000 different log files. This facilitates the need for tools like Elk, Elasticsearch, Logstash, and Kibana to do this log aggregation and full-text search to find these kinds of critical information that I need across my system. Also, integration and load balancing between services becomes hard to do because I might want to run 6 or 7 or 8, however many, replicas of a specific application. But how do I make sure that the load is spread evenly amongst them and that one of them isn't overutilized? Introducing Kubernetes. It's an open source project that's been developed by Google, and it facilitates automation of management of containerized applications, the deployment, and the scaling thereof. So one of the major value propositions of Kubernetes is this fact that it's self-healing. When I deploy an application, I can define certain health checks that Kubernetes will, on specified intervals, keep on checking. If, by some manner, this health check has failed, Kubernetes will go and restart that application for me. It's also very extensible. So there's a very large community working on specific add-ons for Kubernetes, something like internal DNS or perhaps integration with a cloud provider. But what can Kubernetes actually do? It has this thing called a built-in service registry. So you can think of a service registry as a phone book of where can I find services that I'm interested in. But hand in hand with service registries goes service discovery. And service discovery is normally facilitated either by client-side service discovery or server-side service discovery. This is a typical example of server-side service discovery, where as I deploy a service, these instances of that service are then registered with my service discovery out of the box. It also does service internal load balancing, so that problem that I mentioned of if I have multiple replicas of this application running, I don't have to worry about spreading the load equally between all of the services because this is facilitated by load balancing via Kubernetes services, which we'll speak about in just a second. It also does horizontal application scaling. So if we think back, I just mentioned the different types of scaling, but this is on an application level. So if I do find that a specific application is experiencing high load, I can tell Kubernetes, please scale that specific application for me. It also does resource management for you. So this happens on a very granular or on a very coarse level. Within Kubernetes, you get this concept called a namespace, where you can use that namespace to various forms, but it's essentially just a logical grouping of applications. So some people use this to differentiate between different development environments. I might perhaps have one Kubernetes cluster to run a dev and a QA environment in it. Or I might just want to, for some reason, do resource management for all of my monitoring applications because they're so critical. It also allows for various deployment strategies, something like canary deployments or rolling deployments, but we'll speak about that in just a few seconds. It also makes persistent storage management for you very easy to do via static provisioning. If I have perhaps a specific hard drive that I have in my corporate data center, I can access that. And via stateful sets and a whole variety of different Kubernetes resources, it makes accessing and maintaining those storage devices very easy. So there are a few very core Kubernetes concepts that we'll be discussing today. The first of which is called a Kubernetes pod. So you can think of a Kubernetes pod as just a grouping of Docker containers that run together. You can see this P in the background, so you can think of Docker containers as the peas within a pod of actual vegetables. So an example of this would be if I want to perhaps deploy a front-end container which serves some static content like an Angular front-end that needs to speak to some RESTful API, let's say a Java backend. But it's important to notice that, or to take note that the unit of scalability within Kubernetes is a pod and not a container. So if I do decide to deploy these two containers together, if I ask Kubernetes, please maintain 6 replicas of this specific pod, I will end up with 6 times 2, 12 containers. Instead of perhaps I want to scale my front end and my back end separately, then I would deploy them as 2 separate pods. The second Kubernetes concept or resource that we'll be discussing is a Kubernetes deployment. So Kubernetes deployments are used to declaratively define the state and the behavior of the containers within a pod. So the analogy is always made in Kubernetes between cattle and pets. So a pet is something that I care about, something like my dog. I don't want it to die. I actually care about the state of that thing. Whereas with cattle, if one of them dies, it's fine, I'll just start up another one. So pods that originate from deployments are typically seen as cattle. Within a Kubernetes deployment, I also define how many replicas of that specific pod I want to maintain, as well as the specific container that I want to run within that pod. Yet again, coming to the deployment strategies, canary deployments are rather easy to do with Kubernetes via something called proportional scaling. So if I have 10 replicas of a pod running, I can ask Kubernetes, please, this version 1 pod that I have, or application that I have that is running, only deploy 10% of all of those replicas that I want as version 2 of this application. But with canary deployments, it's also very important that if I decide I don't want that version of this application running anymore, that I can easily roll back. And with Kubernetes deployments, it actually keeps a history of all of the deployments that I do. So I've mentioned rolling deployments, I've mentioned canary deployments. So what do I actually mean by that? If you look on the screen, you'll see there's 4 applications running in parallel, all 4 of which are in version 1. But now I ask Kubernetes, I am interested in deploying version 2 of this application. Kubernetes will go, it'll start up, and that application will be in a type of initializing phase, a busy phase. And once it has transitioned to a healthy state, Kubernetes now realizes, wow, okay, you asked me to maintain 4 replicas, but now there's 5. What does it do? One of the previous versions of that application will then be decommissioned, and you'll end up with 3 versions or 3 pods of version 1 running and 1 of version 2 running. And this state right there is a typical example of a canary deployment, where 25% of the users that access my system will now be experiencing version 2 of this application. And if I did decide that, okay, great, I want to move over completely to version 2 of this application, this process will just be repeated until all of the version 1s of this specific application has been deprecated. But why do we actually want to do this? Because now, if I deploy version 2, the users that are accessing my system won't actually notice that I have now completely transitioned onto what is essentially a new application. But let's take Kubernetes out of the picture for a moment. If we were following a microservices architecture without the use of Kubernetes, and I wanted to maintain, for argument's sake, 4 or 6 replicas of a specific service, service A, and another service B, how would I decide where to deploy to in the first place if I have various nodes or hosts that I have to my availability? And how would I make sure that they actually speak to one another properly, they integrate with one another? On the other hand, if my users are accessing this system that I have, this distributed system, how do I make sure that the individual hosts, the individual nodes, aren't overutilized for one of them and the others are sitting idle? So Kubernetes services handle quite a lot of this for you, right? So you can think of a Kubernetes service as just a grouping of pods where network traffic that goes to these pods are distributed. In normally a type of round-robin fashion. So it's typically how in kindergarten you're told 1 suite for you, 1 suite for you, 1 suite for you. This is now just for network traffic. And another word for this is called load balancing. So how do I actually access a service? Kubernetes provides 2 main options for you. One of which is environmental variables that are maintained for you by the kubelet, which is just a Kubernetes daemon process that runs on every host in your cluster of hosts. But the recommended, and funny enough, optional way of doing this is via DNS. So I can, for this Kubernetes service that I've defined, access the application that I've associated with it via a fully qualified domain name. So I don't have to keep track of connection strings the whole time. That happens now via DNS. The last Kubernetes concept or resource that we'll be discussing is Kubernetes stateful sets. So this is intended for use by stateful applications, something perhaps like a database or a message broker. It's very useful for distributed applications, something like RabbitMQ or Redis, where I want to cluster these applications for high availability or perhaps some scalability. And importantly, these pods that get started that originate from stateful sets are named, instead of the name of the application and some random blob thing at the end, it now has an ordinal index that it gets named with. And this is very important if I want to maintain a stable network identity. A typical example of this is with RabbitMQ, where in a cluster of RabbitMQ applications, the identity of a node in that cluster is dependent on the network identity. And for various different types of clustered applications, this becomes very important because I also need ordered pod creation for some clusters. I absolutely have to write to stable storage. A typical example is a database. I want that durability. So that's the technical part of Kubernetes. But how does Kubernetes actually help me with managing my microservices? First off, I don't now have to go decide anymore this specific instance of service A needs to be deployed on this host. Kubernetes does that for you. I don't actually know on which host. I don't care where it runs. It also has this internal service registry, so I don't have to keep track of all of the instances of these applications that are running over X amount of nodes. It also has out-of-the-box internal service load balancing. So I don't have to care, am I actually utilizing all of the instances of these services to their full potential? Also, it facilitates automatic horizontal scaling, so note on automatic. What I can do with Kubernetes is I can say, for this specific application, given a certain policy, let's say, for example, this application, the CPU utilization averages more than 80%. Please start up another application because now I'm experiencing load. It also makes the deployment of monitoring applications very easy to do via a Kubernetes resource called Kubernetes daemon sets, which instead of a deployment where I don't really care where the pods that originate from that deployment runs, with a daemon set, it will maintain one replica or X amount of replicas of that specific application on every host within my cluster. So this is very important if I want to perhaps look into a stream of Docker logs, or if I want to scrape host metrics, something like resource consumption, memory utilization, CPU utilization. Also, configuration is made much easier. So this is facilitated via a Kubernetes resource called config maps and secrets, where secrets are intended for confidential data, something like usernames, something like passwords, something like connection strings. And a configuration map is a deployable entity where I don't have to care in which environment I am. I don't go get dev configuration. I just get the configuration that is there. So where does Kubernetes actually run? Almost anywhere. It has support for bare metal installations, if you want to go install it on your actual a laptop or PC at home. On-premises virtual machines. Hosted solutions. So hosted solutions is essentially just rent a cluster. There are actually companies, something like Stackpoint.io, where you don't care about the underlying infrastructure that it runs on. This comes as a managed service for you. Also on local machines, this is very useful for debugging locally. It's essentially a little virtual machine that I start up where this Kubernetes cluster consists of a single node, where that node functions as both a master as well as a slave, or in the Kubernetes jargon, a minion or node. It also runs on, I think, all of the, or mostly all, of the turnkey cloud solutions, something like IBM Bluemix or Google's GCE or Microsoft Azure, but also on Amazon Web Services, which is the main topic of this talk. So what is AWS? AWS is a cloud services platform that makes the provisioning of IT resources very rapid, and it's very flexible, and it comes at a very low cost. Because of this massive economy of scale, so when I speak about economy of scale, I just mean that there's so much of this resource that it becomes much cheaper, it becomes a commodity. And now I don't have to make that large upfront investment in building my own private data center. It also speaks to affordability from a business perspective. And this applies to startups where I don't perhaps have an exceptional amount of money that I can spend to maintain these servers. And it also speaks to large enterprises that want to gain agility and perhaps decrease cost of these servers that I need to maintain and buy. And as AWS says, friends don't let friends build data centers. So what are the AWS services that we're going to be using to run a Kubernetes application in the AWS cloud? First of which is EC2, or Elastic Compute Cloud, which is essentially the virtual machine offering from Amazon. We'll also be using VPC, or Virtual Private Cloud, which you can see as your own virtual private data center within the AWS cloud. We'll also be using Route 53, which is the managed DNS solution. as well as simple storage service, which is object-based storage that is highly scalable, highly available, and extremely durable within the AWS cloud as well. So let's speak a bit more about EC2. It's, as I've mentioned, fast and easy provisioning of virtual machines that comes in a variety of forms, really. It can be seen as the backbone of AWS. The very first thing when you start experimenting with AWS is normally, I want to start up a machine. And interestingly enough, the first EC2 service was developed locally in Cape Town by the Amazon Development Center in 2005. So within EC2, you get different pricing options or service offerings that they allow. If you just start out with AWS, the first that you'll probably encounter is on-demand hosting. So this is essentially, I need something now, right? A typical example of this would be if I want to prepare for a large amount of load that I know my site is going to be experiencing for a Black Friday sale, for example. Also spot instances, which is a very interesting offering by AWS. So if you think of these Amazon data centers, they're massive, but they're not always utilized to full capacity. So let's say 20% of the specific data center is utilized. 80% you are allowed to go and essentially bid on, right? So you define a bidding price, and Amazon defines a market price. And if your bidding price is above that market price, then that machine is yours to use to your heart's content. But if your bidding price falls below that market price, then they actually take that machine back. This is very, very applicable to something if I want a large amount of computational capacity at very low cost, and my applications have flexible start and end times. Also reserved instances, very similar to on-demand, except I get a discount if I reserve that specific instance for a specific period of time. Also dedicated hosting. So the previously mentioned offerings run within a multi-tenant environment, so I would actually be sharing the physical hardware with other clients of AWS. And this becomes very important when I think of legislative issues. For example, AWS allows a Microsoft bring your own license, with the caveat that you need to run on a dedicated host, according to the Microsoft legislation. It also allows for various family types of instances for specific computational requirements. Something like P&G instances are optimized for massive parallel processing. But within EC2, you get this thing called auto-scaling, where you get automatic scalability by defining auto-scaling groups. And an auto-scaling group is essentially just a grouping of specific EC2 instances. And Amazon makes it very easy to use, because if you use something like an elastic load balancer, as I start and remove instances from this group, it will go and auto-register with this ELB. I can do this automatically as well, based on what is called CloudWatch metrics, which is essentially the monitoring service that AWS provides. But it's actually quite powerful. You don't now only look at memory and CPU. You can look at the amount of requests. You can look at the bandwidth that is used. So I've mentioned automatic scalability, but what does this actually give you? If you think at how you normally model trends, for some reason, people tend to think linearly. This that is currently shown would then be your predicted demand. But as we know in the real world, that doesn't always happen. I might perhaps go through a bit of a dip, and at some point I exponentially receive a large amount of load. And with using AWS scalability or cloud scalability, I get what is called elastic scalability. As my demand increases, I can scale. But compare this to your typical approach of large enterprises, where I have the traditional scale up and scale out approach, where the blue line represents me investing this large amount of capital expenditure in building this data center that I have. But what happens when my load is way down? I'm losing money because I'm not using that asset that I bought. But what happens there, where my computational capacity doesn't meet my load? You just lost your customers. They're experiencing a bad system, a bad service. Route 53 is, as I've mentioned, the managed DNS solution by AWS. And in comparison to other DNS authorities, it's quite interesting how they do this. They guarantee that within 60 seconds worldwide, it will propagate DNS updates to a list of authoritative DNS providers. And magically, they guarantee a 100% availability SLA, which is the only service in Amazon Web Services that guarantees a 100% availability. I have absolutely no idea how they managed to do that. And AWS has recently also become a DNS registrar. So that means I can go and register a domain with them now instead of going through a third-party DNS provider. Alias records, very similar to A records, but alias records essentially map to elastic IPs. And within a cloud environment, you typically don't get guaranteed a specific static IP address. So Route 53 also allows for a variety of routing policies that you can set up. Something like geolocation routing, where a customer accessing my system from America might be routed to an American optimized version of my system. Lowest latency for performance. If I'm in South Africa and I'm accessing a system that's deployed worldwide, I'd probably be routed to Ireland, which is the closest data center to us currently, instead of Tokyo or somewhere like that. Also failover. If I want to use Amazon Web Services for disaster recovery and I have two sites that are deployed where both of them are ready and running, I can, whenever something happens with site A, automatically switch over to site B without my customers noticing. And also your typical routing policy of weighted routing, where I can say 30% of my customers, please use site A, and 70% of my customers, please use site B. The last AWS service that we'll be discussing is S3, so simple storage service. As I've mentioned, this is object storage, not block storage. So you wouldn't use this for something like running a database, for example. You can also do static content hosting. This is very powerful if I want to deploy a very static, very simple website that is immediately scalable. And it guarantees 11 nines durability. So that means I have a very, 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 very bad chance of corrupting data or losing data. And if it's a requirement by a specific organization, you can also use S3 for redundancy via cross-region replication. And AWS S3 was actually designed with a 99.99% availability in mind. I think the actual SLA is only 99.95 only. So how do I actually run Kubernetes on AWS? We can use something called Kubernetes operations. So just to bear in mind, this is not the only way. There are various options, but this is what worked well for me. Or, as it's also known, COPS, which is essentially just CRUD of production-grade Kubernetes clusters within the AWS cloud, and it makes it so easy to upgrade my clusters as well with one line of one executable that I run from a terminal. It uses S3 for cluster state storage, like, for example, how many nodes do I need to run? And if I need to add a node to my cluster because perhaps I want more computational capacity, maybe I have new applications that I'm deploying, I have to run literally one single command via the terminal. One of the major value propositions from COPS is that this Kubernetes cluster that I've deployed, I can export this into what is called a CloudFormation template, which is the AWS infrastructure as code offering. I also need to register a Route 53 domain in order to access this application. So after I've deployed this Kubernetes cluster, where are my applications actually running? Within AWS, they have this thing, or this concept called regions, which is spread out worldwide. And the closest one to us, currently, as I've mentioned, is in Ireland, or Dublin. And within an AWS region, you have this concept of an availability zone. An availability zone in the AWS jargon is what is called a geographically distinct location. For if something happens, say an earthquake, say a fire, then there is backup. So this is how AWS guarantees high availability and failover. So given this Kubernetes cluster that I've deployed into the AWS cloud, what would a typical topology look like? So on screen, we have EU West 1, which is just synonymous with the Ireland region. And within that region, I have currently 3 availability zones. So say I want to, following AWS best practices, want to deploy a Bastion host, which is essentially just a jump box in order to do maintenance and administration on these virtual machines that are running. I can deploy them in a highly available fashion. And this applies to my masters as well, masters and minions within the Kubernetes jargon, because Kubernetes in itself is just a clustered application. So with all of this in mind, go run Kubernetes on Amazon Web Services. Thank you. Thanks, guys.